Chapter 6, Work and Energy. Now, at this point in the semester, you really know all about work and the energy that it requires, right? But now we're going to take a look at the physics definition of work. So, for physics, we say that work is equal to the force times the displacement. Note that this equation requires that the force and displacement are acting in the same direction. We'll get to a more general case in just a moment. But let's first take a moment to try and process, what does this mean, force times displacement? Well, it means that in order to get credit for doing work, like pushing on this car, if you apply a forward force on the car, it only counts as work if you also move the car. So just pushing on the car and not moving it anywhere isn't doing work. Just hitting the wall, assuming the wall doesn't fall over, which we can hope it doesn't, that's not doing any work either. You may have seen this in action when you're doing your homework, for instance. The only way you can get credit is by getting somewhere on the problem. You can put in lots of effort in staring at it, but if you don't go somewhere with the problem, don't put something down, then you can't really get much credit. So that's the idea here, that you're applying a force and you are causing some motion to happen. Now, what are the units here of work? Well, we know we have force times displacement. Force has units of newtons. Displacement has units of meters. So the units of work are newtons times meters, and we redefine those. The newton times the meter is by definition equal to the joule, which is my favorite unit. It's one of the reasons I love my last name, because this is the unit for work and energy, it turns out. So we'll be seeing a lot of joules here, more than just myself. So that's something that you can remember, is that the unit for work is the joule. Now, I mentioned earlier that this equation of the work being force times the displacement only applies when they're in the exact same direction. But sometimes a force isn't in the same direction as the displacement, as the actual motion of path. So what then? Well, let's look at an example to try and explore this. There's a woman here who's pulling a rolling suitcase, right? So her pulling force is at an angle theta relative to the horizontal. It's both forward and up. But the displacement of the suitcase is not forward and up, it's just forward. So what part of her force is actually contributing to this displacement? What is causing the suitcase to move, to be displaced? Well, the only part that's going to contribute to it is the forward part of her force, or the horizontal part of the force. That's in the same direction as the displacement. How do we get just the horizontal part of the force? This is where we go back to components. So vectors pop up yet again. And so we could draw out our force vector on this diagonal at the angle theta, and the horizontal component we could calculate with the overall force vector F, the magnitude of it, times cosine of the angle theta. Because that will give us, this is the adjacent side, so that's why we use cosine here. And that's true throughout the displacement, right? The displacement S is shown here on the bottom. Now, by the way, why are we using S for displacement? Well, some books do use X here, but as we'll see in just a moment, the displacement is not always in the purely X direction. So S is just a more general variable. It's trying to say that this is the displacement in whatever direction it may be. It might be in the X direction, or it might be in the Y direction. So here the work is done by the horizontal component of the force, F cosine theta, times the displacement. And this leads us to our more general equation for the work, assuming you have the work done by a constant force. So for the work done by a constant force, you can calculate with this equation. This one's a great one to use. F times cosine of theta times the displacement S. Now, to get a better handle on it, I'm going to recommend that we check some of the limiting cases, some of the extreme angles for theta. So what happens if the angle theta is 0? Well, if the angle theta is 0, then that tells us that if the displacement is, say, going sideways, then the force must be also going to the right in the same direction. That's the way that we would have an angle of 0 degrees. And in that case, if you plug in cosine of 0 degrees, that equals 1. What pops out? We just have that work is equal to the force times the displacement, which is the first equation we saw. So 0 degrees says they're in the exact same direction. That's fairly straightforward. What about 90 degrees? Well, at 90 degrees, that says that the force is going upward, while the displacement is to the side. With this 90-degree angle, when we plug that in, we get cosine of 90 is 0. In other words, no work is being done. Why is no work being done by this particular force? Well, if the force is perpendicular to the displacement, whatever orientation they may have, that force is not contributing to the displacement. It's not supporting the displacement by pushing in the same direction, nor is it opposing the displacement by pushing in the opposite direction. If it's perpendicular, it's not doing any work in terms of the displacement. That force is potentially causing a different displacement, but otherwise generally not doing work. What about the last case? If the work is instead 100, or the force is 180 degrees from the displacement. So that's the full 180 degrees there. Well, in this case, if you take cosine of 180, you get -1. So that tells us that in our equation, if we plugged into the work equals force times cosine theta times s, you get negative force times s. What does this mean? This means that if your force is pointing in the opposite direction of the displacement, it's actually doing negative work. It's opposing the displacement. So we get positive work if the force is helping the displacement, negative work if it's opposing it, and 0 work if it's not doing anything to change it. So let's look at yet another example of work done by constant force. So here we have someone lifting weights, doing a nice bench press, right? And so if you're doing a bench press, the force that you apply is always upward, right? You're pushing that barbell away from you. You are supporting it so it does not crush you. There's a reason the bench press is one of the most dangerous lifts. So your force is upward. While you are lifting it up away from your body, the displacement is also upward. So force upward, displacement upward. This would have the work, the force and the displacement both in the same direction. So theta here is equal to 0 degrees. So when we plug it in, we get that the work is whatever your pushing force is, your lifting force, times cosine theta times s. So it's just Fs here. Now, once you reach locked out and start to lower it, your displacement's now going down, right? You're lowering the bar. But what's the direction of your force? Well, I hope your force is not pulling it down, or else you might be in trouble. Instead, your force, even as you're lowering the bar, is supporting the bar upward to keep it from crushing you. It's a controlled descent because of that upward force that you are applying. So this upward force is in the opposite direction as the displacement, and that's why we have negative work done, because you are actually taking energy out of the bar, out of its default would be to fall down and crush you. And instead, you are doing negative work to keep it moving at a controlled rate. Right, so that was a nice introduction example. Let's look at a more advanced example. Example 3, accelerating a crate. The truck is accelerating at a rate of positive 1.5 meters per second squared. The mass of the crate is 120 kilograms and it does not slip. The magnitude of the displacement is 65 meters. What is the total work done on the crate by all of the forces acting on it? All right. So here we're trying to find the work done by each of the forces acting on the crate. That suggests we should first figure out what forces are acting on our crate. So let's go through and identify them. So let's see. One of the forces that will always appear is the force due to gravity, the weight of the crate. What direction will that be? That's going to be straight down. Hopefully you have that one down by now. So that's the weight of this. All right, any other forces acting on our crate? Another force is the normal force, right? It's in contact with the truck bed, so that's going to exert a normal force on it. And what direction will that be? It's going to be up, right? Normal to the surface. So this is pretty straightforward. Now, any other ideas of forces that we may have here? Well, there's one other clue here, and it mentions it does not slip. So since the crate does not slip, but the truck is accelerating, that must mean that our crate is accelerating too, that it's experiencing that same forward acceleration as the truck in that positive direction. Well, in order for it to accelerate to the right, there must be a force pushing it to the right. What force is pushing forward or to the right? Well, it's going to be related to the surface, right? And as a clue here, we could imagine, what if the top of the truck was totally covered in ice and then we set the crate on top of that? Would the crate stay on the truck? No, then the crate would fly off the back of the truck because the ice would be too slippery. It wouldn't get enough traction. So what's holding it there is actually the force of friction. It's the force of static friction because it's not moving. So that's a really interesting point. It's one that's easier to miss, but you can, with a little bit of careful thought, we can work our way to getting there. So we want to find the work done by each of these forces. And to do that, we're going to be paying attention to the magnitude of each of the forces times cosine of the angle between the force and the displacement. And then we also already know the magnitude of the displacement is the 65 meters. So we're actually in pretty good shape here. All right, so let's start with the weight because that's our most familiar force. So if we want to find the work done by it, we know that that will be, and here is where I'm glad we can highlight this. Our W's can get confusing, right? I was starting to write the work equation. Work is equal to F cosine of theta times S, but it looks an awful lot like my weight that I wrote over here. So instead of weight, W for weight, I'm going to start always writing mg, just to keep it clear, so that we don't have to get confused there. All right, so for the weight force, I could plug in mg here. Now, what angle would I want to plug in for my cosine of theta? Well, this is going to be the displacements to the right, the weight is going down, so that's an angle of 90 degrees. Now, 90 degrees, cosine of 90, what does that give us? That gives us 0 work. Wow, we can do the same thing with the normal force, right? The normal force is pointing upward while the displacement is to the right. So this is true for both the normal force and for the force of gravity, the weight. So for mg and the normal force. And this is explained on the next slide as well. So the angle between the displacement and the normal force is 90 degrees. The angle between the displacement and the weight is also 90 degrees. So we can clear some of that to make this a little clearer. All right. So we have work done is 0 by those. What about done by this frictional force? Well, in this case, what's the angle? The displacement's to the right, the force of friction's to the right. So our angle is 0 degrees. Cosine of 0 just gives us 1. So the force of friction looks like it's going to be doing some work. The other thing we'll need to figure out is the magnitude of the force of friction. Now, we know that the force of friction can be calculated if it is Fs max, which this problem doesn't really tell us that that would be equal to the coefficient of static friction times the normal force, and we can figure out that the normal force is equal to the weight of the crate. So we can plug that in because we know the mass, but the problem didn't tell us anything about the coefficient of static friction, let alone that this is a limiting case where the crate is about to start slipping. So this isn't going to be our best approach. So how can we figure out how much force friction is causing here? Well, we're going to go back to our favorite equation of the last 2 chapters, Newton's second law. So Newton's second law says that the sum of the forces in the x direction, we'll focus on that here, is equal to the mass times the acceleration in the x direction. Well, what forces are acting in the x direction? Just the force of friction. Awesome. And the mass is something that we know. I think it was 65 kilograms. And the acceleration is also something we know. So we now have derived, using Newton's second law, an equation for the force of friction. This only works for this particular scenario, but once we know that, we can plug it into our work equation. So since we know the angle is 0 degrees, we can find the force of static friction with MA, get 180 newtons there, plug that into our work equation, times cosine of 0, times that displacement of 65 meters. Sorry, it was 120 kilograms, 65 meters. And so this comes out to 1.2 times 10 to the 4th. What units? Joules! So there we have it. So let's look at one last example, think, pair, share type question. So it says some children are practicing catching baseballs. The coach tosses the ball into the air and hits the ball with his bat. The ball travels nearly horizontally directly at the shortstop, who manages to catch the line drive. Did the coach, via the bat, do any work on the ball as it was hit? So there's a bunch of responses here. No, it travels nearly horizontally, no work is done. Yes, work was done on the ball because during the time the force acted on the ball, the bat and the ball moved through some distance. C, no, there was a force acting on the ball, but there was no displacement while the force was acting. D, yes, work was done on the ball because the force of gravity was acting on the ball while it was being hit. Or E, no work was done on the ball because the ball flew even though the force was no longer acting on it. Right, there's a lot to sort through here, figuring out both yes or no and then the reasons why. So think this through, come up with an answer. Once you've made your selection, then you can go on. But until then, please pause the video. All right, did you do that? Okay. Well, let's see. If we think about it, there's this hit that's a force acting on the ball over some distance, right? If we imagine the bat and the ball, and the bat is applying a force, and it's over some displacement while they're moving together. It might be a slight rotation. It might not even be that much of a distance, but the ball definitely is moved and it's in the same direction as the bat. So that does sound like work done to me, right? C says there's force acting up but no displacement. I think the force does also correspond to a displacement. The bat keeps moving, and similarly, the ball starts to move with the bat until it leaves the end of the bat. So it seems like there is work. Let's look at the 2 options for yes work. So D says yes, work was done on the ball because the force of gravity was acting on the ball while it was being hit. The force of gravity was acting on the ball, right? Force of gravity would be pulling down. Now, is that in the direction of the displacement? We said the displacement is nearly horizontally, right? Being hit forward. So it doesn't seem like the force of gravity is moving the ball. That doesn't make sense to me. Let's check the other yes answer. Yes, work was done on the ball because during the time the force acted on the ball, the bat and ball moved through some distance. That seems to match our description. Well, should we go ahead and check? Aha! That was indeed the right answer. So that's exciting. Now, if you got one of the other answers, that's okay. That's not the end of the world. But the challenge now is to figure out why you picked that one and to then understand why that is not the correct answer. It actually can be better if you picked the wrong one to start because you gain a deeper understanding overall in the long run. Now's the time to get it wrong. So even if you got it right, actually, look at the other answers and figure out why you can say, no, I don't think it's that. Get really certain of your answer. This is a time to be learning, to explore, to get messy, make mistakes, right? It's all good. And if you want to discuss this further, please come by my office hours, post in the discussion board. I would love to chat further.